Okay, let's say you have two small balls, each with a mass m, and we put a charge of q, same charge, on both of them. And they are basically hanging from attached to a silk thread with length L and attached to the ceiling point up here. Because of the charge in both of them, these both balls are the same sign, they repel each other and they create an angle theta between the thread and the vertical axis. Now, the question is, what is the maximum amount of charge? Now, in this kind of questions, you have a mass of the ball, which is pulling the ball down. So there is a force of gravity, which is mg downward. And then you will have a electric force, which is in the same line as the line between the two charge, and it's proportional to how much is the charge of these two, and also how much is the distance between them. So you will have a electric force, which is technically k q times q, so it's q squared divided by r to the power of 2. But there's also a tension inside the wire, this thread, T, which, because this reached an equilibrium, it's going to balance what we have on the x-axis and y-axis. So if I find the y components of the t, so t sub y, and if I find a t sub x, then I can use the Newton's second law and say in the x-axis, we will have f sub e minus t sub x would be equal to mass times acceleration in the x-axis. It's not accelerating in the x-axis, so it would be equal to 0. And the y-axis will have t sub y minus f sub g equal to the acceleration times mass in the y direction, but this ball is not accelerating up or down, so the acceleration would be 0, and so this equation would be 0. So we will have two equations to solve together, knowing that this t sub x and t sub y are connected to the value of the tension inside a rib through this angle theta. So you can see that if this angle is theta, thus this angle is theta, and so t sub y simply would be the magnitude of the tension inside the wire, inside the thread, times cosine of theta, and the t sub x would be t sine of theta. Okay, now as you can see, we can also, based on what we can see in this diagram, we can see that a sine of theta in this triangle would be half of the r divided by L, which is hypotenuse of this triangle. And I'm going to use this relationship also to understand what is the relationship between r and then sine of theta. Okay, now let's combine them all together. So we have, from the first equation, we will have k q squared divided by r squared, but I can calculate r from here, so it becomes 2l sine of theta. So I will replace it here with 2l sine of theta to the power of 2 minus tx, which is t sine of theta. Now I can take the tx the other side, and so this would become equal to t sine of x. Then we have t sub y, which I'm going to write it here, t cosine of theta equal to, and then we have f of g equal to f of g, which is mg. Okay, now go ahead and then divide equation 1 by equation 2. So this way, the magnitude of the tension will cancel out. So we will have from the left side, we will have KQ squared divided by 4L squared sine squared of theta times mg, and it would be equal to tangent of theta, sine divided by cosine. So you will have t sine theta divided by t cosine theta, t cancels t, and so this becomes tangent of theta. Now you want to know what is the q, and so you are going to isolate for q in this equation. Okay, I'm going to take the denominator in the left side and multiply it by tangent theta. So k q squared would be 4L squared mg sine 2 theta times tangent theta, and then divide by k and then root a square from everything. So q then would be root square of 4 is 2, root square of L squared is L, root square of sine squared is sine of theta, and then you will have root square of mg divided by k and tangent of theta. And so this would be the amount of charge which creates this particular settings with the angle theta.